Alright, hello guys. This is the recording for 1.2 lesson, solution analysis. Before you do this lesson, make sure that you guys go through the prep for lesson 1.2. It's one problem, it's question number 6, it's part A and part B, and it's using molarity as a conversion factor to get mass and then to get a new molarity. So the answer key is here, and obviously it's on the website. Sit through a solution that you want to analyze. Alright, to review what we did in class, there's this technique called spectroscopy. This technique basically puts light through a solution that you want to analyze. It takes that wavelength information and calculates how much light was actually absorbed and how much light was transmitted through the sample. And based on that, you can calculate the concentration, so how much of something there is in that solution. Now, what is spectrometry and what is it used for? There's lots of different types of spectrometry. In very many disciplines. Google a couple of things. There's a ton, there's thousands of them, maybe not thousands, but hundreds of them. There's mass spectrometry, which we'll talk about later. They use it in astronomy, biomedical research, energy, X-ray spectra. There's so much research going on. One thing that I found that was really interesting was they analyzed blue food coloring, which we analyzed in class, and based on that spectroscopy, they discovered that it is a selective inhibitor, which means that it stops ATP as a form of energy in our body, and it's for a specific PANX1 receptor in cells. Don't know what that receptor does or is, but it selectively inhibits energy release from those certain channels. And if you look down the abstract down here, they think that that blue food coloring could be given for serious consideration for pharmacological intervention of conditions such as acute Crohn's disease, stroke, and injuries to the central nervous system. And so all that wouldn't be possible without spectroscopy. Some other applications of spectrophotometry, spectroscopy, is learning how to make the best fertilizer available for humans to use, formulating the right blend, right? A lot of research goes into spectroscopy. This is some R&D, so research for pharmaceutical companies and drugs. They often use that spectroscopy to make sure that their drugs and the molecules within their drugs are correct, that they are monitored and controlled, they process through it. It saves lots of money and saves lives as well. All right, so that was a quick review of why we study spectroscopy in AP Chemistry. And so now on to the notes. So we're going to look at different types of solution analysis. So part 1, it says understanding Beer's law. And so last year we learned what Beer's law was. And it's basically this equation that allows you to relate concentration to absorbance. And that's what we can use to determine a lot of different stuff about a solution. And so our first question on here says, what is the purpose of colorimetry? When should we use this lab technique, and when are we not able to use it? And so I'm going to go ahead and write copy-paste. Completely screwed up the formatting. Right, so colorimetry allows us to determine the concentration of colored solutions. Right, so if you have certain, like any type of colored solution, if you transmit light through it, some of it will keep going out the other side of the solution, and some of it will be reflected. And so colorimetry allows us to determine how much is reflected, how much is absorbed, how much is transmitted, and that can tell us information of the concentration of that solution. So moving down to question number 2, it says circle the compounds with which colorimetry would be a useful lab technique. So go ahead and pause the video. What do you guys think about it? Alright, so to answer this question now, if it's colorless, light is just going to pass through it, right? Nothing will be absorbed into that solution. And so if nothing's absorbed, then it's completely useless to use a colorimetry process on it. So any of the ones that are colorless, those ones do not count, right? So let me go ahead and strike through those. Right, so any of the ones that are colorless, all of these ones right here, those won't give us any information because light will just pass through them. Nothing will be absorbed, so we won't get an absorbance. And so the ones that are left, those are the ones that are giving us color when we put them in water. So cobalt chloride, copper chloride, potassium chromate, chromate or perchromate. Can't remember off the top of my head right now. Alright, all of those ones right there give us a color solution when we put it into water. So what do all those solutions have in common? And it says to suggest an explanation for the behavior of these compounds that make colorimetry useful. And it says to think about their electron configurations. So pause, think about it. I'm going to move on. If you notice, cobalt, copper, chromate, another chromate, manganese, and nickel, look at the periodic table. Where are they in relation to all the other elements? Those are your transition elements, right? And so they are going to have partially filled D subshells that tend to form colored solutions. Right, so I copied and pasted it right here. So compounds, all of those, the transition elements, if you write out their electron configurations, they all have partially filled D subshells, right? They have, it's like 3D, 4D, and it goes until, not all the way to D10, but it's partially filled because they're right in the middle of that transition area. And so those are the ones that are going to reflect light because the electrons are spinning in such a way that they get excited and they reflect light. There you go. So that's how they get colored solutions. All right, so question number 3 says to state Beer's law and what factors affect the absorbance of that solution and why. So I'm actually going to give myself more room here so I can write it out. All right, so I've written out the equations. So last year we learned this top one right here. So A equals E, it's like a Greek E, epsilon L C. On the AP test, they use the second equation right here. So they use A equals ABC. A and epsilon are the same thing, L and B are the same thing, and then C is the same, and then the big A is the same. So for some reason, the AP test, they give you this equation, but it's the exact same thing as this equation right here. All right, so let's go ahead and name each of these things, right? So the big A, that is your absorption, or your absorbance, I should say. Your little a or your epsilon, so this one or this one, that is called your extinction coefficient. And the extinction coefficient, or the absorptivity constant, that one changes depending on the solution. So that is the one that, even though it says that it's a constant or a coefficient, it will change depending on the solution. So every solution has a different epsilon or A value. All right, the next part on here is the B and the L, so this one and this one. And that is the length of the cuvee. And the length of the cuvee that we used is 1 centimeter, and almost always it will be 1 centimeter. And so that's just the length of the path of the solution through which the light passes. All right, and then the last one, the C's, which are both the same, that is your concentration. And your concentration is the concentration of your solution, how much moles of solute you have in liters of your solution. All right, so when some of those increase, the solution absorbs more of the light, right? So if you have a higher concentration, the solution will absorb way more light. Whereas if you have a smaller concentration, a lower concentration, it's going to transmit light through because it's going to be more colorless, and so light can get through that colorless solution. So those are all of the constants and what they mean. So let's move on to question number 4. Okay, so question number 4 says, how do we determine what wavelength is ideal to use? And so we look at how light is absorbed over all of the wavelengths of visible light. We use the wavelengths at which the absorbance is the greatest. So remember on our spec data on the iPad, we looked at the peak. So that was where we wrote down our absorbance. So we only want to look at the peak. And so if I scroll way down here to this graph, the peak is right here. I'll go ahead and highlight that for you guys. Right, so we're only going to look at the peak of this solution right here. That is where absorbance is the greatest. That's where we want to look for our absorbance data. So question number 5 says the absorbance spectrum of a sample of crystal violet and an absorbance versus concentration graph are shown below. The Cuvier length is 1 centimeter. So if you look right here, this is absorbance on this side, and this is wavelength on the x-axis. And this is for crystal violet. So this is the absorption spectrum for crystal violet. I encourage you guys to look at the Wikipedia page for crystal violet. Crystal violet is actually really cool. It's this chemical. It's also known as methyl violet 10B or hexamethyl para-rosanilin chloride. And it's used in a lot of things, right? It's used in histological stains and Graham's method of classifying bacteria. So this is like way back in the day when they were trying to figure out bacteria things. It's used as a dye in clothing. We can dye it with clothing. It's used in a lot of stuff, medical, veterinary, non-medical things. So I encourage you guys to read the Wikipedia article for it. It's pretty short, but it's quite interesting on what crystal violet is. Okay, so going back to this graph right here. So let's look at question A. It says approximately what wavelength would it be optimal to use for the colorimetry experiment? And so if you look right here at the peak, that is the optimal point. That is optimal wavelength to use because that's where all the absorbance is happening. So if you go down here in kind of a straight line, I would guesstimate that at 600 nanometers. So I'm going to go ahead and write that down. So it's approximately 600 nanometers. That's where we would want to look at the peak. Question B says, what is the molar absorptivity of crystal violet at that wavelength? And so we're going to use our equation A equals ABC or A equals epsilon LC to find that molar absorptivity, to find that extinction coefficient to the epsilon or the A. All right, so I've typed it out right here really quick because my writing utensil is not working properly right now. So A equals ABC or A equals epsilon LC. We're trying to find the molar absorptivity, and the molar absorptivity is just another way to say extinction coefficient. So we're trying to find A, or if you use this equation, epsilon, the big E. So I rearranged the formula. So I divided BC to both sides. So now I have A just by itself. So the molar absorptivity is just by itself. So that way we can just plug everything in and get our answer immediately instead of having to rearrange it at the end. So A, the absorbance right there, if you look up here at 600, we're going to plug in the absorbance for that peak. All right, so I've written down the equation. So A equals ABC or A equals epsilon LC. And so we're trying to find the molar absorptivity, which I have highlighted. So the A or the epsilon, the big E. And I rearranged the equation down here so that way we can just plug everything in and get our answer. So the molar absorptivity is equal to A divided by BC. So I've divided BC to both sides. So in order to get our absorbance, we needed to create an absorbance versus concentration graph, which we put down here. You guys created this in your lab as well. And so every time you did different concentrations of your solution, and you looked at the wavelength with the biggest peak, and you recorded that absorbance, right? So whatever your concentration was, it gave you a different absorbance, but it was at roughly the same wavelength every single time, right? So for most of ours, it was around like the 620-ish range for the blue food coloring. It might have varied a little bit, but that was where the highest peak was. And so for this, the highest peak is at 600. So you did a whole bunch of different concentrations of this crystal violet solution, recorded the absorbance for those different concentrations at that same wavelength, and then they created a graph, absorbance versus concentration. You guys did the exact same thing in your Google Sheets. And so we're just going to choose a random data point right here. So in my example, I chose 3.9 for the absorbance, which is approximately here. So I'm choosing this data point right here. So I'll highlight the data point I'm talking about. We're talking about that one right there. So I just chose a random point on the graph. I could have chosen any of the points on the graph, but that's the one that I chose to use. So 3.9 and the concentration was 12 times 10 to the negative 6. So I'm going to plug that information in. So I needed, right, so A was my absorbance. Oops. So A was my absorbance right here. And I chose on the graph to use 3.9 for that. B was the path length of the cuvee, and they told us that the cuvee is 1 centimeter. So I'm plugging in 1 centimeter right there. And if you look at the graph again, since we chose that absorbance, go down to that concentration, and it's 12 times 10 to the negative 6 moles per liter, which that is the units for concentration. Multiply and divide all of that out, and you end up with 3.3 times 10 to the 5th liters times, or over moles times centimeters, right? So the negative 1 right here for both of the moles and the centimeters just means that it's being divided on the bottom, right? So it's liters divided by moles and centimeters. So don't forget your units. That is usually 1 point if they give you this type of question, especially for the molar absorptivity, because molar absorptivity units usually change. So make sure you guys get your units down. Right, and it's just the centimeters and the moles and the liters right here. Right, question C says, what is the crystal violet concentration of a solution with an absorbance of 0.050? Right, so same thing. I'm using the A equals ABC or A equals epsilon LC. I rearranged it for C, which is concentration. So I divided AB to both sides, and so that way I can just plug everything in and not have to worry about rearranging the equation later on. So absorbance, it says, is 0.05, so that is our given. So we're plugging 0.05 in right here. We know our molar absorptivity, that's our A or epsilon, and so we're going to plug that into the equation, right? These are connected questions. And then the last one is B, which is the length of the cuvee, and the cuvee is 1 centimeter. So plug all of that in, multiply, divide, and you get 1.5 times 10 to the negative 7 moles per liter. And those units make sense because that is what concentration is. And then there you go. All right. For part 2, the molecular view of solubility, you need to memorize your solubility rules. I will give you a quiz within this next week on your solubility rules and your polyatomic ions. So you need to memorize your solubility rules. They do not give those to you on the AP test. So I wanted to draw these out, but my computer is acting a little weird, so I'm just going to explain each of these. And so this is the teacher edition notes online, and I'm just going to talk through them. So part 2, so number 6, it says sketch a particle diagram for aqueous solutions for each of these substances. Include a few molecules of water as the solvent. So remember, water is a solvent. And it says provide an explanation for your sketch. Include a chemical equation in your explanation if applicable. And finally, predict whether the solution will conduct electricity and explain briefly. So silver chloride, if you remember, silver chloride is one of those that is not soluble. So remember, go back to your solubility rules. I gave that to you on the very first week. It's in one of your handouts. There's also a YouTube video on the website. So silver chloride is not really soluble. So it is an insoluble salt. And insoluble salts, they stay together, right? So my sketch, I have silver chloride, and they stay together. They do not break apart in water, so they stay together. And I put positive, negative, right? Make sure you don't put two negatives together. Make sure you don't put two positives together. They always alternate positive and negative. Your equation for this is they break apart like a stupid tiny amount, right? They're insoluble, so they're not going to break apart very much, but sometimes they do. And so we're going to say that silver chloride, back and forth arrows, silver plus chloride minus, right? And so if you wanted to, you can even make the arrow going back towards the silver chloride solution, going back this way to the left. You can make that arrow bigger, and then the one going to the right really tiny. So if it is insoluble, there's no ions in that solution, right? They can't really conduct electricity because they're stuck together. They're not free moving, right? So electricity usually occurs because there's free ions, free electrons moving around. And so silver chloride is will not conduct electricity because they don't have any ions in that solution. They don't have enough ions in that solution to conduct any electricity. This one right here is nitric acid. Right? Nitric acid is a strong acid. Go back to memorizing your strong acids and your strong bases and your solubility rules. Right, so nitric acid is a strong acid. Strong acids, we know, dissociate, break apart 100%. So our sketch of that is going to show hydrogen ions floating about and nitrate ions floating about. And when we write out the equation, it is 100% dissociated, so there's only one arrow right here going to the right. So it completely breaks apart into hydrogen and nitrate. And so since you have floating ions, floating positive and negative ions, you're going to have free movement of electrons, and that will conduct electricity because there's a ton of ions in the solution. Calcium chloride is also soluble, and so it breaks apart completely 100%, dissociates, and so you're going to have calcium ions and chloride ions. And this should actually be a chloride ion. I'm sorry, that was a typo. Right, this hydrogen right here, go ahead and cross it out. That should be a chloride. That's a typo. I'll fix the formatting of it later. But notice that it's a 1-to-2 ratio, right? There's 1 calcium for every 2 chlorines, 1 calcium for every 2 chlorines. This should be a chlorine. And so that needs to be represented in your picture and in your equation, so make sure you balance them. And since this is 100% soluble, it breaks apart. There's positive and negative ions floating around, allowing electrons to move freely. They will conduct electricity because there are many, many ions. All right, this right here is methanol. All right, so CH3 there's 1 carbon, that's a meth group, and the OH is an alcohol, so this is methanol. It is polar, right? So the OH, if you draw the Lewis structure of this out, is polar. It has an uneven distribution of electrons, but it doesn't break apart. It is not an ion. It is a it is a polar covalent molecule, and so it sticks together. So when you draw it, you're going to draw the whole molecule like this. Right, so that's methanol, and it's a polar molecule, so it will mix in water, right? Like dissolves like. If you have an OH group in water, both of them are polar. They will mix together, and so when you have a methanol solution mixed with water, it just looks like water. You'll be able to smell that it's methanol, but it just looks like water. So that's what miscible means. It just mixes together. It won't conduct any electricity because there's no ions, right? There's no positive charges, there's no negative charges. Electrons aren't allowed to move very freely, and so it won't conduct any electricity. The next one, KOH, right? KOH is a strong base. It ionizes 100%. Strong bases and strong acids do that. And so you're going to have K+, so potassium ions, OH-, hydroxide ions in your picture. It breaks apart 100%, so we're just going to have 1 arrow right there. And it will conduct electricity because there's free motion of electrons with those ions floating around in water solution. All right, hydrofluoric acid, that is a weak acid, and so it ionizes very, very little. All right, so some of them you're going to draw as HF together, and some of them you're going to draw as H+ and F-, right? So weak acids, that means that it breaks apart a tiny, tiny bit, but not like a strong acid where it breaks 100% apart. So hydrofluoric acid, we're going to have 2 arrows, back and forth arrows right here, and you're just going to write it just a normal acid equation, so HF breaks apart into H+ and F-, but it prefers to be as HF, right? Hydrofluoric acid, it prefers to be together because it's a weak acid. And so it will conduct a little bit of electricity because there are a couple of ions floating around, right? There's positive and negative ions, but for the most part, there's more of these HF together, and so it will conduct a tiny bit of electricity, but not a lot of electricity. Question 7 says, what factors determine how well a substance dissolves in water? So if a substance dissolves well, it's either a soluble salt, so memorize your solubility rules. It is a strong acid or strong base. There are 8 of each of those, I believe. Double check me on it though. Memorize those. They will not give them to you on the AP test. Or if it is a polar molecule compound or weak acid. So if it's polar molecule, it will mix. It doesn't necessarily dissolve, but it's miscible. And a weak acid will dissolve a tiny, tiny, tiny bit. Insoluble salts, they don't really dissolve very much. We write the equation, so going back really quick, AgCl, we write the equation as if they dissolve, but in reality they don't really dissolve, which is why in our sketch we drew them together. So last year in honors I said that they didn't dissolve at all. We didn't write any dissociation equation. In AP they do dissolve a stupidly tiny amount. It's like less than 1%. So we have to write the dissociation equation, but in reality they do not conduct electricity, they do not break apart, so our sketch is going to keep them together. Right, question 8, it says what factors determine how well a substance conducts electricity? A solution conducts electricity well if the solute ionizes 100%. So if they break apart 100%, you have cations, you have anions, and so it's going to have that positive charge, that negative charge. It's going to allow for free motion of electrons. If you have free motion of electrons, it's going to conduct electricity. That is what electricity is. And then the second part to that says a solution conducts a little bit if the solute ionizes a little. So like weak acids. Right? So weak acids, they conduct a tiny, tiny, tiny bit, but not very, very much. And then lastly, a solution does not conduct if the solute does not ionize, such as insoluble salts or molecular compounds, right? So like silver chloride, that was an insoluble salt. It's not going to conduct any electricity because it doesn't have any cations or anions, or not enough anyways to make a difference. And molecular compounds such as methanol, so CH3OH, methanol is a polar compound, a polar molecular compound, and so it will mix with polar molecular water, but it doesn't dissolve in each other. So they just mix because they're both polar and they attract each other, but they don't ever dissolve in each other and they don't create ions, they don't create free-flowing electrons. All right, again, I wanted to draw this out, I wanted to write it out, but my computer's acting really weird. So part 3 says a molecular view of concentrations. So we want to get how much you have of this thing, this chemical, this compound, in water. So that's what we're going to talk about for question number 9. So it says consider a solution that contains copper 2+, represented by the particle diagram to the right. Right, so this one right here, so it has water, it has 4 copper ions in it. A sample of solution was placed in a calorimetry at 635 nanometers, and an absorbance of 0.86 was reported. Right, so we put this solution right here into a calorimeter. We record the solution at the highest peak, and the highest peak in this case was 635 nanometers, and the absorbance at that peak was 0.86. So that is what this solution right here gave us. So question number 9 says, suppose water was added to the volume of the solution is doubled. So we added water, right? So if you can see the water changed. So none of the ions disappeared. We still have 4 ions, but the water was just added. And so that's called a dilution. So if you add water to blue food coloring, it gets lighter and lighter, right? So if you keep adding more and more and more water to, like, say 1 or 2 drops of food coloring, it's going to get lighter and lighter and lighter and lighter. Right, so it says sketch the particle diagram for the resulting solution. Right, so that's this on the right-hand side. So we added more water, but there's still the same amount of copper ions. So the concentration of that part hasn't changed. Right, and it says what has changed? Justify your answer. So the moles of copper hasn't changed, right? We go from 1, 2, 3, 4 to 1, 2, 3, 4. So the moles have exactly stayed the same. We have 4 moles of copper, 4 moles of copper. That hasn't changed. The volume of the solution has changed, right? Because we went from halfway to completely full in this beaker that we're using. So we added more water, so the volume increased. And the concentration changed, right? If you remember the equation for concentration is molarity, and molarity is equal to moles divided by liters. So even though the moles didn't change, the liters changed, right? So if you increase the amount of liters, it's going to decrease your concentration, right? And that makes sense because if you add more water, it's going to become a lighter colored solution, right? So go ahead and write out the equation m equals moles over liters. If you increase the denominator, the liters, that's going to give you a bigger fraction. If you get a bigger fraction, it's going to decrease the overall amount, so it will decrease the molarity, right? So that's the concentration. So moles stayed the same, volume increased, and therefore concentration decreased. If a sample of this new solution is placed in a cuvee, run through calorimetry, what would be its expected absorbance, right? And so that one, you're going to have to write out the equations. A equals ABC, plug everything in, and figure it out. I'm going to let you guys try to do that one by yourself, but the answer should be 0.43. All right, question B says, suppose half of the volume of the original solution was spilled. Sketch what it would look like. So we spilled this top beaker right here. So this was the original volume, or the original solution. We spilled half of it, right? So if we spilled half of it, half of our copper ions are gone, half of our water is gone. And so our volume changed, and our moles changed, but the concentration didn't change, right? If we have half gone of the moles and the volume, they're going to be equivalent, right? So this is 2 divided by 2, pretend, and this is 4 divided by 4. So even though half was spilled, the concentration stays the same. And then C, and go ahead and calculate the sample as well, right? That one shouldn't be an issue. If it stayed the same, the absorbance will be the same. So it should be 0.86, right? And so C, it says, suppose half of the volume of the original solution was evaporated. Sketch the picture, a particle diagram for the resulting solution. So if half of our water was evaporated, so we just heated it up, or maybe we left it out for too long, half of our water is gone, but the copper isn't gone because copper is too heavy to evaporate, so just the water is gone. So we still have the same amount of moles. We still have 4 coppers. Right, so the moles did not change. The volume definitely changed, right? It decreased. And if you change the liters, so remember molarity concentration is molarity equals moles divided by liters. If you decrease the volume, so if you decrease the denominator, it is going to increase the overall fraction, and so it will make the concentration increase as well. Right? So if you decrease liters, it will make molarity increase. And if it increases, right, it's twice its solution, so 0.86 times 2 is going to be 1.72. So that's the new absorbance of it. Right, so hopefully the overview of the notes helped you guys. I tried writing on the paper like I usually do in class, but my computer is acting a little strange right now, so I kind of had to just talk through it. Hopefully it still helps though. So there's 6 questions for your homework, or the problems, and then there's 1 AP question from 2003. Memorize your solubility rules, memorize your strong acids, memorize your strong bases. Memorize which ones conduct electricity, right? That's based on all the solubility rules and the strong acids and the strong bases. And learn how to use Beer's law equation. So they give that equation to you on the AP test. That is on the equation sheet. They use big A is equal to ABC. It's the same thing as big A is equal to epsilon LC. And molarity, right? So those are the major things right there that we kind of talked about. There's intermolecular forces, there's ions. I mean, there's a whole bunch of underlying knowledge that you guys have to make sense of this. So hopefully the problems shouldn't take you too long. They're pretty easy. I believe the answer keys are already on the website. And then make sure you do the quick check. And once you've done the quick check, practice your net ionic equations. I will probably give you guys a quiz on your solubility rules, your polyatomic ions, and your strong acids and strong bases sometime during this week. And we're moving on to stoichiometry as well this week. So text me on the Remind app if you have any questions about 1.2 lesson, but it's all based on Beer's law, knowing how to read the graph, and your solubility rules, and your strong acids and strong bases. All right, have a good rest of the day whenever you're watching this.